Okay, so I'll be taking analog and integrated circuits for this semester. Hope I am audible. So I'll just share my screen. Are you able to see the slides? Yes or no? Okay, so we'll just start the introduction about operational amplifiers. Already you must have studied this in your S3 circuits. What is an op amp? So this subject completely deals with operational amplifier. So the first module is about the basics of operational amplifier. So basically ICs, integrated circuits, are classified as linear integrated circuits, that is LIC, and digital integrated circuits, that is digital ICs. So these are the main classification of any IC, linear and digital. So what is the difference? Linear ICs means it accepts the analog input and deliver, or the output is also analog. Some examples are, the first one is operational amplifier, op amps. In short, we say op amp. Then another IC is triple five timer IC. This also we will see in the last module. Then PLL IC, phase lock loop, voltage regulator, that is 723 IC, etc. etc. Whereas digital ICs, you have already done your digital, that is logic gates 7400, 7404, where the digital output is digital. You have only 1 or 0. Multiplexers, microprocessors, all these comes under digital IC. So where it accepts the input in two discrete voltages, that is logic 0 and logic 1. Output is also discrete with two specific voltage levels. So that is the two classifications of integrated circuit, linear, and that is linear ICs and digital ICs. So here in this subject we are dealing with linear ICs, LIC, or analog IC. That's why the name analog and integrated circuits. So 741, that is the op-amp, the operational amplifier. 741 IC is a linear IC. So what is an operational amplifier? You must have studied the block diagram. I will show you the block diagram first. Okay, this is the basic block diagram of any typical op-amp. I hope this you must have studied. It has 4 blocks. First is the input stage. Second is the intermediate stage. Third is the level shifting stage. And the last is the output stage. So basically, operational amplifier is a direct coupled high gain amplifier consisting of one or more differential amplifier. So you know what is a differential amplifier. So it has, the first is the input stage, which is a dual input balanced output differential amplifier. The second stage, which is called the intermediate stage, is again another differential amplifier, which is a dual input unbalanced output. So the difference between these two, say this is a dual input balanced output differential amplifier. Here it is a dual input unbalanced output differential amplifier. So that's why it is called consisting of one or more differential amplifier. It's a direct coupled or DC coupled high gain amplifier consisting of one or more differential amplifier. Then the next stage is a level shifting stage or a level translator. So we'll see what is the purpose of this level shifting stage, followed by an output stage. So the last stage is a complementary symmetry push-pull amplifier or an output stage. And op-amp can be used to amplify both AC as well as DC signals. An operational amplifier, or in short op-amp, can be used to amplify both AC as well as DC signals. And why the name op-amp? Because it was initially designed for computing mathematical operations such as addition, subtraction, multiplication, integration, etc. So that's why the name comes as operational amplifier, or in short op-amp. So this is the basic block diagram of any typical op-amp. Okay. If you have anything, any doubts or anything to ask, you can interrupt me in between. So this is a basic differential amplifier. You must have, I think it was there in your last module of your S3 circuits. A basic differential amplifier. So what is the main purpose of a differential amplifier? It amplifies the difference between the two input voltages. You have two inputs, V1 and V2, and it's a common emitter configuration. And you can see it is symmetric also, symmetrical. And you have two supply voltages, plus VCC and minus VE. So the main purpose of this differential amplifier is to provide high gain to the difference mode signal. So you have two inputs, V1 and V2. So it amplifies the difference between the two input signals, V1 and V2, and cancel the common mode signal. Common mode in the sense when you have the same input signal at the input of both the, that is at the input at the base of both the terminals. So the main purpose of the differential amplifier is to provide or is to amplify the difference mode signal and cancel the common mode signal. So that's what is called common mode rejection ratio, CMRR. This also you must have heard about. What is CMRR? So it's the ability of the op-amp or the sensitivity of an op-amp to a different signal as compared to a common mode signal. That means it should provide or it should amplify only the different signal and it should cancel the common mode signal. So that ability or that sensitivity of the op-amp is called common mode rejection ratio. And it shows the figure of merit of the differential amplifier. So from the name itself, it is clear, CMRR, that is common mode rejection ratio. That is how well it can reject the common mode signals. how well it can reject the common mode signal and how better it can amplify the different signal. So it should provide high gain to the different signal and cancel the common mode signal. So that ability or that sensitivity of the op-amp is called the common mode rejection ratio, CMRR. So this is an important parameter of the op-amp, or it indicates the figure of merit of the differential amp. So higher the value of CMRR, we can say better is your op-amp. Higher the common mode rejection ratio, better is your op-amp. Also another requirement of a good op-amp is that it should have high input impedance. So this is basically a differential amplifier. So this is the symbol of an op-amp. It has two input terminals. You can see these differential inputs are designated by plus and minus sign. Plus indicates it is the non-inverting input. Minus indicates it is the inverting input. So what do you mean by non-inverting input? Here V1. V1 is designated as the non-inverting input, which means that any signal, any AC or DC signal applied to the non-inverting input produces an output which is in phase with the input. So that is what is called non-inverting input, V1. And V2, that is the inverting input, which means that any AC signal or DC voltage applied to the inverting input produces an output which is 180 degree out of phase. You can see the outputs. Input and output are 180 degree out of phase. So output voltage is 180 degree out of phase with respect to the input signal. So that is what is meant by inverting input. And A is called the large signal voltage gain. So this is the symbol of an op-amp. It has two input terminals, inverting and non-inverting inputs, V1 and V2, and one output terminal, that is V0. So here, which is the inverting and non-inverting input? Here you have B1 and B2. B means it is the base, actually, base of this transistors Q1 and Q2. So how do you know that which is the inverting input and which is the non-inverting input? So you can see the output. See, the output is a balanced output. So that means it's measured at the collector of the transistors. So V02 minus V01. So that means you are measuring at the collector of Q2 with respect to the collector of Q1. You are measuring the output at the collector of Q2. And you know that there is a 180 degree, this is a common emitter configuration. There is a 180 degree phase shift between collector and base. So when you, that is, where the B2 will be, the terminal B2 will be the inverting input terminal, because there is a 180 degree phase shift between this V02 and the base B2. So this V2, the input V2 will be the inverting terminal, since the transistor Q2 provides a phase shift of 180 degree for the output taken at the collector of Q2. This transistor Q2 provides a 180 degree phase shift for the output taken at the collector of Q2. So that's why we say that B2 will be the inverting terminal, and of course B1 will be the non-inverting terminal. Okay, so that's how you differentiate between inverting and non-inverting terminal in a differential amplifier. In a differential amplifier, here B2 is taken as the inverting terminal because there is a 180 degree transistor Q2 provides a 180 degree phase shift for the output when it is measured at the collector of Q2. And of course, B1 will be the non-inverting term. Now, so differential amplifier can be used in 4 different configurations. The 4 different configurations are depending on the number of input signals, and also it depends on the way the output is taken. So there are 4 configurations: dual input balanced output, dual input unbalanced output. So dual inputs, and the first 2 cases are dual input. Dual input means we have 2 inputs. The last 2 cases are single input. Single input means you have only 1 input, balanced and unbalanced. So if we use 2 input signals, the configuration is said to be a dual input. What we have seen in the previous figure, because we have 2 inputs, V1 and V2. So this is a dual input. And so otherwise it is a single input configuration. That means if we have only 1 input, it will be a single input configuration. Then if the output voltage is measured between the 2 collectors, it is referred to as a balanced output. So that is also what we have seen in this figure, balanced, because the output is measured between the 2 collectors. The output is measured between the 2 collectors. That's why it is called a balanced output, because both the collectors are of the same potential, same DC potential with respect to ground. So that is what is balanced output. Now what is unbalanced output? If the output is measured at one of the collectors with respect to ground. So at one of the collectors with respect to ground, then it is unbalanced output. The configuration is called unbalanced output. So that is our intermediate stage, the second block. The first block is a dual input balanced output. The second is a dual input unbalanced output. So that is the difference between, these are the 4 configurations. Differential amplifier can be used in 4 different configurations depending on the number of input signals. That means whether it is dual input or single input, and depending on the way the output is taken. That means balanced output and unbalanced output. That is, the output voltage is measured between the 2 collectors. It is called balanced output, and if it is measured at one of the collectors with respect to ground, it is called unbalanced output. Now this is a dual input balanced output, because you can see 2 inputs, Vin1 and Vin2, and then balanced output because it is measured between the 2 collectors of this differential amplifier. The output is measured between the 2 collectors. So that's why this is called dual input balanced output differential amplifier using constant current bias. So the difference here is from the previous figure. You can see from the previous differential amplifier, from this differential amplifier you can see this resistor RE and VEE. RE and VEE are replaced. This portion is replaced by a constant current bias. You can see here this emitter part, this RE and VE are replaced with using a constant current bias. So in the differential amplifier, the combination of RE and V is used to set up the DC emitter current. So this is a constant current bias which is used to set up the DC emitter current. So constant current, that means we can use a constant to set up the DC emitter current. That means the emitter current IE. And this constant current bias provides the current stabilization. So you can see a transistor and three resistors R1, R2, Re. R1, R2 forms a divider. So this provides this acts as a constant current source. So let's say it is using a resistive. This is a resistive constant because we are using resistors R1, R2 and Re. So this is a resistive constant current bias. And resistor Re is replaced by a transistor. So here you have a transistor Q3. A transistor Q3 is provided. So the DC, this DC collector current Q3, this IC3 is established by these resistors R1, R2 and Re. Now, so this is one way of providing a constant current bias. Now, another way of providing a constant current is using current mirror. So, what is a current mirror? You must have already heard about this. What is a current mirror? Current mirror means it is a circuit in which output current is forced to equal to the input current. You have an output current and an input current, and both these currents are made equal. So this current mirror is a circuit in which the output current is forced to made equal to the input current. Current mirror is a circuit in which output current is forced to equal the input current. So this is how, this is a circuit of a current mirror circuit. You have already studied this current mirror. I am just refreshing it again because this is the output current IC3. The current of Q3 is forced to made equal to the input current I2. This output current is forced to made equal to the input current I2. So it is a special case of constant current bias. So our aim is to make the DC emitter current constant. So this is another option using a current mirror because it provides a constant current bias. And it can be used to set up a constant emitter current in the differential amplifier stages. Okay, so this current mirror can be used to set up a constant emitter current in differential amplifier stages. So that is another option. You can that is instead of using a resistive constant current bias, you can go for a constant, you can go for a current mirror circuit also. So what's the third stage, third block? After input stage, intermediate stage, you have a level translator, the third block. So what is the purpose of level translator or a level shifting stage? So as I have told, because of the direct coupling or the DC coupling, the DC level at the emitter increases from stage to stage. And as we go back to the block diagram, you can see the third block. Yes, you have input stage, that is dual input balanced output, intermediate stage. So it's a direct coupled, DC coupled. So after this intermediate stage, the DC level at this output increases. It rises from stage to stage. So you have to bring down the DC level to 0. For that you are using a level shifting stage. And level shifting stage is nothing but an emitter follower using a constant current source. So that is the circuit what we are going to see, level translator or a level shifting stage. So purpose of this level shifting stage is to bring down the DC level downwards to 0 volts. So that is, we have three options or three circuits. The figure A, it's an emitter follower with a voltage divider. Emitter follower with a voltage divider, because input is given here, output is taken at the emitter used with a voltage divider. Then the second one is an emitter follower with constant current bias. So here the two diodes are used to provide the instead of the resistor. So this provides a constant current bias. The same emitter follower, the only thing, this resistor is replaced with a constant current bias, and in the third one it is replaced with a current mirror. Again the emitter follower with a current mirror which provides a constant current bias. So the purpose of this level translator is that we have to bring the DC level, because the DC level increases from stage to stage. This increase in DC level will shift the operating point and it will limit the output voltage swing. So also the output should have a quiescent voltage level of 0 volt. That means when you have 0 input signal, output should also be 0. But it may not be so. So you have to bring down the DC level to 0 volt. For that we are using level shifter. So level shifter or a level translator is nothing but to bring down the DC level to 0 volt. So it is basically an emitter follower with a constant current source. Emitter follower, you can see here these transistors are emitter follower with a constant current source. So that is the third block in the block diagram of the op-amp. The third block is a level translator or a level shifting stage, which is nothing but an emitter follower with a constant current bias. An emitter follower with a constant current bias. And it can also act as buffers to isolate the high gain stages from the output stage. And the last stage is the output stage, the fourth block. And what is the function of the output stage or the purpose of the last stage? So the function of the last stage, that is the output stage, is to supply the load current and provide a low impedance output. To supply the load current IL and to provide a low impedance output. So we are using the emitter follower with complementary transistors. So this is Q1 and Q2 are complementary transistors which provide very low output impedance, and it also supplies the load current to the output. So that is the output stage or the final stage. So these are the four blocks. The four blocks in a typical op-amp. The first stage is an input stage, which is a dual input balanced output differential amplifier. Second stage is a dual input unbalanced. So here you can see, since it is unbalanced, you have only, it is measured at one of the collectors with respect to ground. Unbalanced output. So that means it is measured at any one of the collectors with respect to ground. So these two are differential amplifier stages. And after the intermediate stage, since the DC level rises above 0 volt, you have to bring down the DC level to 0, downwards to 0. So for that, you are using a level translator or a level shifting stage, which is nothing but an emitter follower using a constant current source, followed by an output stage. Output stage provides or it determines the current supplying capability of the op-amp. Output stage is nothing but a complementary symmetry push-pull amplifier. So it provides low output, it should provide low output impedance, and also the current supply should provide the load current to the output. So these are the four blocks in a typical op-amp. Any doubts? So the main, the most commonly used op-amp is 741 op-amp, which we will be doing the lab also in this semester using 741 IC. So using the 741 IC, you will be doing your the op-amp, that is I think electronic circuits lab. So this is an 8-pin IC. 741 is an 8-pin IC. This is the pin configuration of 741. You should be familiar with this pins. It's an 8-pin. So you can see here which are the inputs. 2 and 3 are the inputs. Inverting input and non-inverting input. 2 and 3 are the inputs. And the output is 6. Pin number 6. 2 is the inverting input. 3 is the non-inverting input. And 6 is the output. So you have 2 input terminals and 1 output terminal. Then you have the supply voltages, that is you have positive supply voltage plus VCC and the negative supply voltage minus VE. So 4 and 7. 4 and 7 are the negative and positive supply voltages. So op-amps are available in 3 packages, that is metal can package, dual in DIP package and ceramic flat package. You can see the figures here. This is just some general information. Metal can package, dual in, that is DIP package. This is the metal can package and this is the DIP, dual in line package. So it is an 8-pin IC. And the temperature ranges also, because it is manufactured in 3 temperature ranges for commercial purpose, for industrial purpose and for military purpose. So C indicates, if you write 741C, C means it is commercial, I indicates industrial and M for military purpose. And mu A, that is, it indicates the manufacturer name. Mu A741, mu A indicates the manufacturer is Fairchild. You have other manufacturers also. This is the number. C indicates it is the temperature range or commercial. A means it is the package. So then the power supply, how do you, it's a dual power supply IC, because we have both positive and negative supply. So how do you connect it? When you wire also in the lab also, how do you connect this positive plus VCC and minus negative supply? Because 741 is a dual power supply IC. It needs plus VCC and minus VCC of 15 volts. Because we are using a differential amplifier configuration. So 741 needs 2 power supplies. And they are to be connected as shown in the figure. So how do you connect this? Your plus and minus are shorted and you ground this. And this is taken as the positive supply and this negative is taken as the negative supply. So this is how do you do the connections. Otherwise the IC will be damaged. If the polarity of the voltages is not given properly, the IC will get damaged. So the first thing when you do the lab, please ask how to, or please learn how to connect the dual supply. So this is the way how it has to be connected. Otherwise, your IC, your op-amp will get damaged. So dual supply has to be given properly, especially the polarity of the voltages. If it is not given properly, the IC will get damaged. Because you have both, it's a dual op-amp or dual. So it has both positive and negative supply. So 7, pin number 7 is for connecting plus VCC and pin number 4 is for connecting minus VCC. Any doubts? Because we have to see some electrical parameters of the op-amp, some of the parameters, some of the electrical parameters of the op-amp. Or yes, these are the parameters we have to see. So we have seen the classification of IC, we have seen the block diagram of the op-amp and the internal circuit. We have seen the block diagram. We have seen that there are 4 blocks and what is the circuit inside. We have differential amplifier, we have level translator, electrical parameters, input offset voltage, input offset current, input bias current, input resistance, input capacitance, offset voltage adjustment range, drift, CMRR, this is one important parameter, common mode rejection ratio, PSRR, that is power supply rejection ratio, gain bandwidth product, and slew rate. So we have to see the definitions of what are these parameters and what are the typical values for 741 op-amp. So first we will see what is input offset voltage. These parameters are important. So input offset voltage, you can see the op-amp symbol. This is, we have 2 inputs, the 2 differential inputs minus the inverting input and the non-inverting input, then V0 is the output. So ideally we say that when there is no input, output should be 0. If we have not applied any input, ideally the output should also be 0. But practically output may not be 0. So the input offset voltage VIO is defined as the voltage that must be applied between the 2 input terminals of the op-amp. So you can see here we are applying 2 voltages, V1 and V2. So it is the difference. Input offset voltage VIO is the difference or is the voltage applied between the 2 input terminals of the op-amp to obtain 0 output voltage. To obtain 0 output voltage, we are applying 2 voltages V1 and V2. And input offset voltage VIO is the difference between V1 and V2. To make the output 0. To make the output 0. Because ideally the output of the op-amp should be 0 when the inputs are grounded. That means if you directly ground this input, if you directly ground both inverting and non-inverting input, ideally the output should be 0, but practically output is not 0. Due to mismatch between the parameters of the differential amplifier, it can be due to many parameters, that is mismatch between the differential amplifier pair. Output may not be 0. So you are applying 2 voltages V1 and V2 to make the output 0. So VIO is the difference between V1 and V2, that is V1 minus V2. And 741, the value of VIO is 6 millivolts. Ideally, what should be the value? It should be 0. Ideally, VIO, input offset voltage, should be 0. But practically, it is not 0. It is 6 millivolts, very small voltage for 741. So the maximum value of input offset voltage VIO is 6 millivolt for 741 op-amp. And for 714, this is another op-amp which is called precision op-amp. Better op-amp, 714, has a smaller VIO, 150 microvolts. So That means lower the value of VIO, better is your op amp. Lower the value of input offset voltage, we can say better is your op amp. That's why this is called precision op amp. 714 is a precision op amp because its input offset voltage VIO is less, 150 microvolt, whereas 741 the input offset voltage is 6 millivolt. Okay, just 2 minutes, I will come in. Any doubts you can ask? Any doubts? Otherwise, I will stop here. I will continue tomorrow. Let me take the attendance. Ardra SV. Sorry, this is a B batch. Joel John.
Present, Miss.
John Subin.
Present, Miss.
John Subin.
Present, Miss. Present, Miss.
Julia George.
Present, ma'am.
Ananya Ramesh.
Present, ma'am.
Ananya Ramesh.
Present.
Kannan. Kannan. Absent. Karina Alexander.
Present, ma'am.
Kashinath.
Present, ma'am.
Kiran P. Nambiar. Kiran P. Nambiar. Absent. Nasif.
Present, ma'am.
Madonna.
Present, ma'am.
Manas MV.
Present, ma'am.
Nisab.
Present, ma'am.
Muhammad Amin. Muhammad Amin. Muhammad Hasan. Muhammad Hasan. Muhammad Raneem.
Present, Miss.
Muhammad Shehzad. Shehzad. Absent. Tashbir Ali.
Present, Miss.
Muhammad Rayhan.
Present, Miss.
Shan. Muhammad Shan. Muhammad Shan. Absent. Navaneet.
Present, ma'am.
Naslul.
Present, Miss.
Naslul. Naveen.
Present, Miss.
Neeraj.
Present, ma'am.
Niranjan.
Present, Miss.
Yeah. Nived Shiva.
Present, Miss.
Noel Shiji.
Present, ma'am.
Parthiban CK.
Present, ma'am.
Parthiv KR. Pranav OV.
Present, ma'am.
Pranav P.
Present, ma'am.
Prince Thomas.
Present, ma'am.
Unyayam.
Present, ma'am.
Rahul P. Rahul P. Absent. Rishabhadev. Rishabhadev. Sanjana.
Present, Miss.
Sanjay Krishna.
Present, ma'am.
Saurabh Sadish.
Present, Miss.
Sawad.
Present, ma'am.
Chomia.
Present, Miss.
Sibin Raj.
Present, ma'am.
Siddharth P.
Present, ma'am.
Suryajit K. Suryajit K. Saurav C.
Present, Miss.
Sridevika Prasad.
Present, Miss.
Shruti S.
Present, ma'am.
Tamanna. Tamanna. Absent. Tashbiha. Vaishnav. 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 Vandana.
Present, Miss.
Vinaya. Vinaya. Ismaya.
Present, ma'am.
Vrunda. Akshay Pramod. Akshay Pramod. Abdul Rahman. Abdul Rahman. Muhammad Aslam. Muhammad Shadin.
Present.
Saeduddin. Sri Lakshmi NS.
Mr. Shan, present, ma'am.
Surijit present.
Okay. Okay, we'll see tomorrow.